Alright, we are just reviewing concepts from yesterday. If you weren't here, which I think everyone was here in this period, we're looking at cube rooting as opposed to square rooting. Please remember your index, so please put a 3 in that little index place. Now, with fractions, as with square roots, we have to split up our radicand such that we are cube rooting both the numerator and denominator, and then simplifying from there. So, we're going to cube root the numerator and cube root the denominator. Remember, with cube roots, it is possible to have a negative, so what I'm going to do is just rewrite that with a negative on the outside. Cube root of 6 divided by the negative cube root of 125. If you plug 125 and raise that to the 1/3 power, you'll see that that is a perfect cube. So what you'll end up with is the cube root of 6 divided by negative 5. Do you have any questions about that? It does not matter if you put the negative in the numerator or the denominator, just not both. Because remember, two negatives cancel out when you're dividing them. Or you can just put it on the outside, which is the most common. So you can rewrite it like this. The C is there the whole time. Okay. Thanks, Alyssa. Okay. Let's move on to the next one. Alright, so I kind of messed this one up last time, but basically with cube roots in the denominator, you're trying to find something to multiply the radicand by to get a perfect cube. Something to get a perfect cube. So we saw, for example, when we had the cube root of 32 in the denominator, that we wanted to multiply that by the cube root of 2 to get 64, which is a perfect cube. So you always want to try to get that perfect cube. Well, with x squared, I just have to multiply it by 1 more x to get an x cubed, which is a perfect cube. So that's what I'm going to do. Okay, so 2 divided by the cube root of x squared times the cube root of x divided by the cube root of x. Remember, our product property says that we can take those radicands and multiply them together. So I end up with my numerator of 2 cube root of x divided by the cube root of x cubed. The cube root of x cubed is just x. And then I just am left with 2 on the outside. Because this was on the outside originally, I have to leave it on the outside. So 2 cube root of x over x. Questions? Yeah, 2 more things to look at. More concepts. We're going to look at conjugate pairs. I would just write down that first sentence. What a conjugate is. This is a continuation of 9-1. We will finally be done with 9-1 after these notes. It says, the binomials a root b plus c root d and a root b minus c root d, where a, b, and c and d are rational numbers, are called conjugates. You can use conjugates to simplify radical expressions that contain some or difference involving square roots in the denominator. Essentially what conjugates, the concept that they revolve around, has to do with something that we looked at last chapter, and those special fractions and special products. For example, we said that whenever we have a squared minus b squared, what does that factor into? That factors into some sort of special factor. What does that factor into? We don't have a middle term. We don't have a 2ab. What do you think? We just learned a plus b, a minus b. So what we're trying to do is form this here so that we get this, and these squares get rid of our square roots. I know that's a little confusing, but when I multiply by the conjugate here, I'm multiplying by 2 plus root 3 in the denominator and 2 plus root 3 in the numerator. The reason that I do this, again, is that I have that plus and minus so that I can end up with squares, and these square roots will cancel out. So in other words, when you multiply by the conjugate, we'll go ahead and multiply the denominator. You're going to have to distribute that to each term. And that numerator. So when you take that numerator and you multiply that 7 to each individual term, you end up with 14 plus 7 root 3 on top. On the bottom, if you know your special factors and special products, when you have something like this, you'll end up with this, a squared minus b squared. So it's going to be 2 squared minus the square root of 3 squared. You could, of course, do the distribution to get that, but again, we really want to make sure that you have those special products down and understand how they apply. So again, I multiplied by the conjugate. The conjugate just means if this is a minus, I want a plus. I have the same terms, but I just have a difference in signs so that I end up with some sort of special product. Okay. Now, when we simplify this, we end up with 14 plus 7 root 3 divided by 4 minus 3. When you square a square root, they just cancel each other out. They're inverses. So 4 minus 3, which is just 1. So you end up with 14 plus 7 root 3. So whenever you see a plus or a minus here with a radical, and you know you have to rationalize that denominator, you have to multiply by something called a conjugate. Conjugate pairs make these special factors. Special factors allow us to get rid of the roots. Question? Here's some practice problems if you're watching the recording. So pause the video, take a moment, and try them. We're about to discuss the answers. So, number 19. What is the conjugate pair to root 5 minus 2? Root 5 plus 2. So, I'm going to take that, my original problem, and I'm going to multiply by root 5 plus 2 in my numerator and in my denominator. I have to distribute that root 13 to each term. Now, what you want to do here is you already know that when you take root 13 times root 5, you're going to end up with root 13 times 5. We learned that the other day, right? Break this down if you can. Well, use it as part of a factor tree, 13 and 5. Since they're both prime, I can't break that down any further, right? So, I'm just going to leave out root 65. So I have root 65 plus 2 root 13. So root 65 plus 2 root 13 over. Now your special product rule says what squared minus what squared. Root 5 squared, right? Root 5 squared, or the square root of 5 squared, minus what squared? Yeah, 2 squared. In the numerator you have root 65 plus 2 root 13 divided by 5 minus 4, which is just 1. So your final answer is just root 65 plus 2 square root 13. Do you have questions on that, and does it make a little bit more sense what I did? The next one. What's the conjugate pair to root 2 plus root 7? Yeah. Root 2 minus root 7, or square root of 2 minus square root of 7. So, multiply that numerator by root 2 plus root 7. Oops, sorry, minus. As well as that denominator by root 2 minus root 7. Okay, when you perform the distribution, you're just leaving 12 on the outside. 12 square root 2 minus 12 square root 7 divided by, okay, what am I going to square? What's going to be squared? Square root 2 and square root 7. Well, remember, squares and square roots cancel out. So in the numerator, I'm left with 12 square root 2 minus 12 square root 7 divided by 2 minus 7. So I have a negative answer. I have negative 12 root 2 minus 12 root 7 all over 5. I just took that negative and put it out. Do you have questions, or does that make more sense? Yes. Yeah, negative 5. I just put the negative up front. Any other questions? Like radicals. So now we have to add and multiply them. So I would just write down that first sentence again. What are like radicals? And then those two examples. Okay. This says, performing operations with radicals. Radicals with the same index and radicand are called like radicals. Just like terms. You can add and subtract like radicals the same way you combine like terms by using the distributive property. All this means is, unless they have the same index and radicand, you can't add them. So either you need to make it that way by simplifying your radical, or if you can't simplify them, then you just have to leave them alone. So for example, for the first one, I can combine the 5 root 7 and the 8 root 7 because the root 7s are the same index and radicand. 5 minus 8 is what? Yeah. So that root 11 can't combine with anything because it doesn't have a like radical. And then you have a minus 3 square root 7. On the second example, they don't have the same radicand, but they have the same index. So we're going to have to simplify that radical to see if we can, in fact, get the same radicand. So that's 4 and 5, 2 and 2. So the square root of 20 simplifies to be 2 root 5. So in this case, I now have 10 root 5 plus 2 root 5. So what do I have? 10 root 5 and 2 root 5 make 12 root 5. You're combining the like radicals like you would your like terms. X plus x makes 2x. AB plus AB makes 2AB. So 10 root 5 plus 2 root 5 makes 12 root 5. So you're either simplifying to get like radicands, or you're just, as is the case with 11, just leaving it alone because you can't break it down. Alright, any questions about combining like radicals while adding or subtracting? Treat them like terms. If there's anything you get out of this part of the video, treat like radicals like terms. They're not any different. Like radicals. So what do I get? 8. 8 cube root 3. Yep. 8 cube root. Okay, multiplying radicals can be a little tricky in the sense that you can't just multiply them and be done. You have to simplify if you can. So 5 to 3 make 15. And then 5 and 75. That will make, what do we get? 375. Now, you can't just stop there. You gotta simplify it. That one, 15 is 5 and 3. I can't break that down. Right? 375, I can break down. So I'm going to look at 375. And I already know that 375, it already gives me some of my factor figures, 5 and 75. So that's 15 and 5. Yeah, 15 and 5. And then that's 3 and 5. So, what do I have here? I have the root 75, 375. That equals, with my product of times, 3 times 5 times 5. 3 times 5 times 5 times 5. Okay, so this simplifies to what? Yep, because you have an index of 2. So I have what on the outside? 5. I have 1 pair of 5. And what on the inside? 15. So, guess what? I can combine root 15 minus 5 root 15. So that's like 1 minus 5, which is negative 4. So this is negative 4. Let me let that soak in. Alright, here are a ton of practice problems if you're watching this video with the answers included. These can be very difficult, So I'm going to do number 27. So, I have a special product. You could do the distribution if you wanted to, the FOIL form. But you should remember that 2 root 5 minus 4. Again, I can't emphasize this enough. You need to know your special product integral factors. If I have a minus b squared, what's that going to be? A squared minus 2ab plus b squared. So I have to apply that same logic here. Square this minus 2ab. So 2ab, that's going to be 8 root 5, right? You just got to memorize this. Go home and memorize it if you don't have it memorized already. Plus 16, because I squared that before. All right, this one is tricky. When I square this one, I'm squaring the entire thing. So it's 4 times 5. What did I do? 2 squared is 4. Root 5 squared is 5. Okay? Minus 16 root 5 plus 16. Well, 4 times 5 is 20. Oh, root 5. Thank you. So, thanks, Addie. 4 times 5 is 20. 20 plus 16 minus 16 root 5. 20 plus 16 is 36. That's where they got that 36. Minus 16 root 5. We're going to take all day on Monday to practice these. I know it's hard. Okay. If you're watching the video, here's your table of contents.